Let us look at the molecular interpretation of work and heat. And as we are dealing with statistical thermodynamics, we already know that the average energy of a macroscopic system, U, is given by the probability of the particle being in state J multiplied by the energy of the state J. This summed over all the states. Right? So sigma J, Pj, Ej. That is what I'm talking of. So, and probability we know Pj is given by this simple formula which we've seen from the very beginning, e to the power minus beta Ej by Q. Okay. Now, if you look at this equation, then what we see is that the energy U happens to be a function of two variables, the probability and the energy. So I could see that the change in energy can then be written as the change in the change in U, the average energy, can be written as a sum of the change in the energy of the states times Pj being held constant, and or I could either change the probability of these states by holding the energy of the states constant. This is like saying that I have one function which is dependent on two variables x and y. I hold variable x constant and change variable y and see the effect on the function, or I hold variable y constant and change variable x and see the effect on the function. The total change in the function would be the sum of these two. Right? So this is what this particular statement tells you. The total change in the internal energy U is the sum of changes in the energy states or the occupancy of these energy states. That is the probability. Right? What is the probability of these states? Let us just not worry about capital N. Let's hold it fixed. So let's worry about a closed system. It's much easier. Later on, we'll worry about open systems where the number of particles or the number of moles can be changed. So if you look at dEj, then so Ej was a function of n and v, and we are holding n constant. So Ej happens to be only a function of the volume v. Right? If you remember how Ej comes about, it comes about as n square h square by 8 ml square, right? And for a three-dimensional system, we had taken the a square and then gotten a volume from there. So if I change the volume, the energy levels change, right? If I increase the volume, the energy levels would come closer. If I decrease the volume, the energy levels would be far apart. Yeah, think of a ladder. Okay, so these are, each of these rungs happens to be an energy level, and so the ladder, the rungs come closer or the rungs go away from each other as I change the volume. Okay, but if dEj is, well, if Ej is dependent on volume V, then dEj would be dependent on the change in volume, that is dV, right? So this equation I can then further write as du is equal to sigma Pj dEj by dV times dV plus sigma Ej dPj. Okay. Now I am getting close to things which I know. Yeah, I know that du, du is equal to W plus Q. And now if I look at W, then I know it is, well, du is not W, sorry. It is delta W plus delta Q. And now if I look at this one, then I know this is minus P dV plus delta Q. I compare this particular terms with the equation above and I see that this is nothing but delta W and this is nothing but delta Q. Yeah? The dV gives out this reasoning. Okay. So what essentially is work? Yeah. Work is something what we've defined as the energy change when the volume of the gas changes. That's my mechanical work. There are many different kinds of works that can be thought of. You can have chemical work, you could have electrochemical work. So you have a surface work. Here we are talking of mechanical work. So minus PdV is very easy. But what is happening? Is the probability changing in this particular term? Or is it the energy? You see clearly it's not the probability, it is the energy. dEj by dV. And what I just talked about was, if I'm going to change the volume of this, if I'm going to decrease the volume of the system, I'm going to increase the energy level spacing, right? So I'm not changing the probability, I'm not changing the population of these particles. Still, the same number of particles are being occupied as was being occupied earlier. Only thing is that because I've made the volume smaller, the energy levels have now separated out further, and whatever was there in the higher energy levels is still there. So totally the energy of the system has increased. Yeah, the gas has compressed, work has been done on the gas, energy has been pumped into the gas. How does it accommodate the energy? It accommodates by changing its energy levels, increasing the spacing between these energy levels, right? Not changing the occupancy of these energy levels. But look at this fellow. The energy levels are not being changed, but the probability is being changed, right? The energy levels remain the same. If I heat the system, then some of the particles which were in the lower lying energy states, they jump to higher lying energy states. I change the probabilities over there. This is the difference, the major difference between work and heat, right? Okay, so yeah, we can write work and heat like that. Well, yeah, of course, we've been using minus PdV, so better we call it reversible work and reversible heat, right? That doesn't matter, that doesn't change the understanding of it. Okay, this is up to this point we've already discussed. I've just told you the difference between how work changes the energy, the internal energy of the system, and how heat changes the internal energy of the system, right? Now if you see, delta W reversible, we know it's minus P dV, and we also know that it is this fellow. Right, so let me equate these two. So if I put that, then pressure is given by sum of Pj del E by del V, right? Or minus the average of del E by del V holding n constant. We've used this result earlier. Go back and look lecture 15. We'd used this result to evaluate PV is equal to nRT for an ideal gas. An important result. We'll be using it quite often. We've used it earlier, right? Okay. There's another thing that I would like to introduce you to, and that is the concept of enthalpy. Okay. Enthalpy is nothing but its energy. Okay. Now, if I look at delta U is the internal energy of the molecules or atoms or gas molecules in general. We are talking of mostly of gas molecules, but yeah, in general, it could be any system, right? So we have internal energy, and we know that it's given by the heat exchanged and the work done, and I could write that as Q minus, well, if I'm talking of reversible systems, Q minus PdV integrated from V1 to V2, right? Now, if I were to work with constant volumes, then this work done goes to 0, right? Since dV is 0, constant volume. So what I'm left with is delta U is equal to QV. That's how I defined the change in internal energy, and that's how we normally measure the change in internal energy by doing an experiment in a closed vessel. We supply the heat, and the change in energy is then given by the heat supplied at constant volume. What you need for this is a closed vessel. It's called a bomb calorimeter. Okay, but if you look at most processes that are occurring in nature, they're taking place at a constant pressure. So instead of using a constant volume, it would be more useful if I were to account for energy changes at constant pressure, right? And if I look at constant pressure over here, then what I would need is QP. Okay, so I could use the same equation, Q plus W is equal to delta U, or Q is equal to delta U minus W, or I could use delta U plus P. Now P is being held constant, so I cannot use P dV where I can change the pressure. So P external, V1, V2 dV. Okay, so P is being held constant. I'll use one particular P, and then I can get delta U plus P external dV. So this leads me to define another quantity which is the equal of delta U plus P dV. I would define something like enthalpy, which is H equal to U plus PV. Okay. So when we are talking of constant pressure, then delta H is equal to delta U plus P delta V is equal to QP. Okay. So this is just for definition. I can use definitely any values of pressure over there. Okay. Now, let us try to understand what this enthalpy is and how it is different from the internal energy. Well, it's the internal energy plus P times delta V, and physically what does it mean? Let's take a look at these two examples, and the concept of delta H should be much more clear over here. So think of an example, melting of ice, okay, at 0 degrees C. Then we're going to do it for 1 mole. So we'll use these delta H bar, delta U bar everywhere. So bar denotes a molar quantity. It is nothing but the heat measured at constant pressure. So if you want to do a heat measurement at constant pressure, you do it under some given pressure conditions. Usually if you're doing at 1 atmosphere, you could do it under a normal calorimeter. Now we know that for ice, the delta H at constant pressure, so heat exchange at constant pressure, delta H, is given by is equal to 6.01 kilojoules per mole, and this is experimental value. So I want to evaluate delta U, which is nothing but delta H minus P delta V, and delta V is the volume of liquid minus volume of solid. So liquid is the final thing, solid is the initial thing. I'm melting ice, right? So what I get over here is 6.01 kilojoules per mole minus, I do that at 1 atmosphere. The pressure is 1 atmosphere. This is the volume, molar volume of liquid. This is the molar volume of solid. Not much difference actually, if you see. So there should be hardly any difference in this value. 1 atmosphere into 0. This minus this comes out to be 1.6 into 10 to the power minus 3. That's already in the third decimal place. I'm sure it's not going to make any difference. And then convert from liter atmosphere to joules. There you go. And then from joules to kilojoules. So you have a 10 cube factor over here. And this fellow would be a 10 square on the top. So if I don't do anything else, then it's about 1.6 into 10 to the power minus 4. Right, it's 6.010 something. So it's approximately 6.01 kilojoules per mole. There is hardly any difference between delta H and delta U for the melting of ice. This essentially dependent on P delta V, right? Okay, let's look at the second example. Vaporization of water at 100 degrees. And I know the delta H is given as 40.7, and delta V now is a very large number, 30.6 liters per mole is the volume of water vapor at 1 atmosphere. And again, I can use the same 0.0180 for liquid, which is negligible. It's approximately the same. I say delta V is roughly 30.6. Well, if I were to use this for an ideal gas, I could actually write delta V is equal to delta N RT by P. Yes. So delta N would be the change in number of moles. So this equilibrium, if I would have written, as hydrogen liquid going to hydrogen gas, and so let me put something over here. So this is what I'm looking at, and if I'm looking at this particular equation, then the change in the number of moles, right? The change in the number of moles happens to be gas minus liquid, that is 1. So delta V bar, if I were to assume it as an ideal gas, is nothing but delta N, which is 1, and RT by P. I could have used that also. Should come out more or less similar. If it doesn't, then of course the numbers are not correct. Don't worry about that. I'll not check it out here. But what I get is delta U, which I'm looking for, and delta U comes out to be 37.6 kilojoules per mole. Now delta U is essentially the change in the internal energy. What is that internal energy? Huh? It's the hydrogen bonding between these water molecules, right? It is the kind of interaction that would exist between the molecules in a liquid state. And in a gaseous state, I'm taking these molecules apart. So delta U happens to be this intermolecular interaction between the molecules in the liquid state. That's 37.6. But delta H happens to be a bit higher. That is because the rest of the energy, 3.1, is consumed to increase the volume from 0.0180 to 30.6 liters per mole. Right? So you need 37, so out of 40.7, you need 37.6 to overcome the intermolecular forces, and another 3.1 to increase the volume against the constant atmospheric pressure. Right? All right. I will leave this lecture with an exercise for you, and you need to prove Cp minus Cv is equal to Nr for an ideal gas. Okay, Cp is given by delta H by delta T at constant pressure, and Cv is given by delta U by delta T at constant volume. Alright, see you in the next class.